Hi, everyone. I'm pleased to be able to speak with you, even under these grim conditions. So first, a little bit of background. Much of my research has dealt with hazards. A lot of these projects have included things like wildfire in Mediterranean scrub, um, the um, Northridge earthquake, and a group of projects I called disaster by management. And some of the projects have been 9/11, Katrina, and the Columbia crash. Another emphasis is biogeography, especially wildfire ecology in Southern California, and documentation and conservation of California sage scrub. My teaching load includes courses in hazards and risk management, biogeography in California ecosystems, and multivariate statistics. So how did this background get me to Mars? In the late 90s, I was working on a project on how the then new internet was being used by two activists to create a large social movement to stop the Cassini-Huygens mission. NASA got wind of my project and invited me to present it to 5 of its centers in 2001. They were interested in learning how better to communicate risk for the Mars sample return lander mission that was then being planned for a 2008 launch. So the telecon organizers asked me if I would follow that controversy. I agreed and decided that maybe I should learn about Mars to have a context. So meanwhile, MSR kept getting delayed and was eventually canceled. So by 2005, I was left with no project and a whole lot of hard-earned background on Mars. So rather than forget it all, I created the first Geography of Mars class in 2007. So I thought at least our students would get something out of all that. So a lot of my Mars work since then has been driven by course development. So what about APXS? I innocently thought that I would just put together all of the APXS data from all 4 rovers and then have students do a K-means clustering and Google Earth mapping lab with those data. So I got the APXS data from the PDS Geosciences node as a series of CSV files that had been uploaded there periodically by the different teams involved. Each with very different layouts and formats. So this took a lot of pre-processing to integrate. And then pinning APXS zaps to latitude and longitude was really challenging with different datums and cartographic conventions and who knows what datum it is that Google Earth uses. So my goal was to have students do a simple classification that they could then map in Google Earth Pro, maybe 4 or 5 categories. I picked K-means clustering as it is a non-hierarchical and really flexible method. It optimizes the, let me move this down. It optimizes the allocation of data to a specified number of classes. And so it first seeds the data space with proposed centroids, usually randomly. And then it measures distances between each record and all the seeds, assigning it to the nearest seed. Once all records are assigned, the centroid for each group is calculated and then used as the seeds for the next iteration, producing changes in some records, cluster assignments. And the process is eventually truncated once the assignments become pretty stable. So once records are classified, they can be mapped fairly easily in a Google Earth in Google Earth Pro. Google Earth only needs to have a name for the record and its latitude and longitude, and you can also put the records into folders corresponding to the classes. So it can import CSV files, which can then be saved as a native KMZ file that can be opened by anyone with Google Earth or Google Earth Pro. And so in the previous page, I provide links to the, oops, not just yet. In the first page, I had links to the KMZ file. Okay, now, so this was the goal, this rather simple exercise for my students, but for me to understand the variability in the data to help them interpret the results, I did all kinds of behind the scenes classifications in this software package PAST for K equals 10, K equals 20. Sometimes I did them data reduce with PCA. And I eventually settled on K15 with standardized data, which is what I'm going to talk about today. So there are 8 steps to the workflow. I downloaded the PDS Geosciences node files on all 901 APXS readings that were available from July 1997 through November 2016. And so I got them integrated into one common database, which I did in OpenOffice Calc. I then geocoded each record, and this was a real nightmare. Fred Califf at JPL graciously fielded my barrage of questions and shared waypoint files with me. Once these records were individually geocoded, I standardized the oxides and the elements abundance data for each record against the means and the standard deviation for all 901 records in Calc. So then these T-scores, I moved into the package PAST and did the K-means clustering for the K15 request. So after that, I calculated descriptive statistics for each standardized oxide and element in Calc for each of the 15 clusters in order to be able to characterize their patterns of enhancements and depletions for each cluster. So after I became comfortable enough with this to be able to shepherd students through it and walk them through the process of mapping their work in Google Earth Pro, I became interested in the K equals 15 classification. I had created a common cluster system to compare and contrast each of the 4 rover sites against one another in a single common classification scheme. Another topic of interest was visual comparison of the 15 clusters diagrams, and noticing that the clusters seem to fall into 5 broader groupings that I call metaclusters. And so the clusters in each one of these metaclusters falls along trends of exaggeration. And so these kind of imply a series of origins and aqueous alteration pathways. So the results, so I'll walk through the metaclusters. So cluster 7 formed a 1 cluster metacluster that I call X for exogenous or potentially exogenous. Some of the targets that were grouped into this cluster were iron meteorites. Others were not iron meteorites, but they share that strong elevation in zinc. I mean, not in zinc, in nickel. And nickel enhancement can be a result of hydrothermal alteration of olivine-rich basalts, and that is consistent also with the elevation that you do see in zinc and in magnesium oxide. So clusters 6, 8, 15, and 5 form metacluster B for basalt. These graphs you can see hew very closely to the Martian averages with very little variation above and below. So cluster 6 seems to show virtually no departure at all from Mars norms. Cluster 8 shows a few slight excursions, and these are consistent with picritic basalt. This cluster was really common on the floor of Gusev crater. Okay, cluster 15 seems to represent the admixture of local basalts with the elevated iron and magnesium oxides that you see in the global dust. And then this last cluster, cluster 5, is often interpreted as unaltered olivine, meaning no contact with water. But then there are cases in which proximal materials in this class seem to form a source and sink relationship where groundwater or hydrothermal fluids precipitate iron oxide and magnesium oxide in the form of carbonates. Clusters 3, 2, and 10 form metacluster E for potentially evolved magmatic materials. Cluster 2 was, which is in the middle here. Cluster 2 was first spotted at the Pathfinder Sojourner site, and it was deemed andesitic because of its elevated silica signal, as well as depressed iron and magnesium and calcium oxides. Alternatively, however, this profile could result from neutral or alkaline water interactions with primitive basalt, which can liberate, mobilize, and concentrate silica. Chapter 3, Cluster 3 seems more unambiguously to be fractionated material with very strongly elevated alkali oxides and aluminum oxides in slight elevation in silica. And a Cluster 10 resembles Cluster 3, but it is a little bit more exaggerated, and it also shows additional elevations in the oxides of phosphorus and titanium. And this cluster is unique to the area around Husband Hill, and it has been interpreted as pyroclastic tephrites. Clusters 1, 12, 9, and 11 are grouped in metacluster N, standing for signs of a neutral or a neutral alkaline water alteration. So all of these show enrichments in chlorine and bromine in various ratios. Cluster 1 shows little departure from the Mars norms, very similar to just garden variety basalt, but it has elevation in chlorine and also in bromine. Cluster 12 shows a stronger pattern of chlorine and bromine excursions. Then in Cluster 9, you have those two also quite strongly elevated, but you also have a zinc signal and a weak magnesium oxide signal. Cluster 11 has spectacularly elevated levels of chlorine and bromine, as well as high levels of the fluid mobile zinc, manganese oxide, and magnesium oxide. It should be noted that this cluster has 5 targets out of the 901, so I think we're looking at small sample effects here. Clusters 4, 13, and 14 come together in metacluster S, and they represent aqueous alteration in acidic water, which raises the signal of sulfur trioxide, which is the only sulfur species that APXS can pick up on. Cluster 4 is pretty close to the Martian averages, again, your garden variety basalt, but with a slight spike in sulfur trioxide. Cluster 13 exaggerates this. And so you see a strong elevation in sulfur trioxide. And you also get a magnesium oxide, manganese oxide being slightly overrepresented. Cluster 14 is very much like 13, and it exaggerates the elevations and depletions of cluster 4, but unlike 13, it shows truly spectacular elevation of calcium oxide, and this has been interpreted as calcium sulfate. And I have to admit, on the abstract 1262 at LPSC, there's a typo in there. For some reason, I put down carbonate when I meant sulfate. So, and LPSC won't let me fix it at this point. Okay, so then I've plotted the means of all of the targets in each metacluster, and you can clearly see their distinctive personalities. You know, here's the sulfur-enriched series, and here's one that's potentially evolved materials. They show very different personalities. Now, the metaclusters can themselves be sorted into 3 different target origins, 2 of volcanic character and 1 possibly exogenic. The overwhelmingly most common one, of course, is basalt. And there may also be more fractionated materials. And then, of course, you get the occasional meteorites. Okay, now given its commonness, basaltic materials are the ones that reveal signals of water alteration. Okay, so the more unambiguously pristine basalts are seen here on the left side, showing little to no contact with water. But on the right, you see them bifurcating into two alteration pathways. And the upper ones entail signs of neutral or neutral alkaline waters, most likely groundwater, but sometimes surface water too. And these are marked by different levels of the halogens and by their relative balances. The lower pathway suggests alteration in acidic conditions with elevation of sulfur trioxide. And the final cluster shows the concentration of calcium oxide, suggesting calcium sulfate. Now, the evolved materials is a little more ambiguous. Cluster 3 seems to be pretty clearly fractionated materials running along the alkaline series, sometimes compared to terrestrial mudgerite. Cluster 2 is a little more ambiguous. This is the one that was thought to be andesite when it was first encountered in Chrysoplanitia, but it may also entail aqueous alteration in neutral water. 10 is confined to Gusev crater, and it is an exaggeration of cluster 3, and it's usually attributed to tephrite. But the fractionation argument is not universally accepted. It's been argued to show the formation of Montmorillonite clays in alkaline waters. And so exogenous materials are, of course, a lot harder to spot other than the really obvious iron meteorites. So any stony iron or stony meteorite may never be detected, especially if they did undergo aqueous alteration. So I believe this is the first attempt to integrate all readings from one instrument, APXS, that was common on all 4 rovers in a common inductively developed classification system. This common classification now can be used to compare the 4 sites in the same terms. And so of the available 15 clusters, only 2 were found at Pathfinder. 12 were found by Spirit in Gusev crater, 13 by Opportunity in Meridiani Planum, and 11 by Curiosity in Gale crater. Now, the allocation of the metaclusters among the 3 rovers with large enough numbers of APXS readings is highly significantly different in a chi-square test. So highly significant, and also with a moderately strong effect size. You've got the Kramer's V of 0.41. And so using this test and comparing and contrasting the 4 sites, Gusev crater is basalt dominated. And it is somewhat impoverished in the acidic aqueous altered materials. Meridiani Planum is dominated to a pretty strong extent by these acidic modified materials. And Gale crater tends to be low on the acidic modified materials and high on the neutral water altered materials. And it is also pretty underrepresented in basalts, which created space for those other, for the evolved materials and the neutral aqueous materials. Okay, let me fast forward just a second before I get to Google Earth, because I know that's going to be fun. I mentioned that I had done this for a class, and so I want to show you what the student labs, how they came out. So I've got my classifications on the top and the kids' classifications on the bottom. So each student was asked to do a K=4 classification. And then I combined the 16 students' efforts into one database. and found that 5 classes emerged, and they actually map pretty closely to my metaclusters. But you'll notice that an awful lot of detail is lost. So if you go straight to k equals 4, what you get is the algorithm is going to classify an awful lot of stuff as basalt, including those materials that show very subtle signs of alteration by neutral or by acidic water. So my suggestion is if you use k-means classification, use a higher K request and then regroup your results visually into the smaller number of categories that you're really interested in working with to be able to detect and retain those kinds of subtle changes. And so, so the outcome of this too is I wanted the students to map the results in Google Earth Pro. Their maps were actually pretty hilarious, but I'm not going to get into that. So if you would like to see the results of the K15 classification, you need to have Google Earth or Google Earth Pro. And then you download 2 KMZs. The first one is the KMZ that I created from the K15 classification. Now, what about the other one? The other one has to do with a problem in Google Earth. Google Earth shows trajectories for the different rovers, and the ones for Spirit and Opportunity are quite accurate. Those are the ones that were done in the GIS lab at Ohio State. But the Curiosity trajectory is insane. I mean, it shows the rover going straight up and down cliffs. I mean, it's really quite funny. So someone named Fernando Nogal did this as a labor of love. He has reconstructed the actual path of the Curiosity rover and made it available as a download from unmanned spaceflight. And so if you use Google Earth to look at these targets in Gale Crater, you should have his KMZ too. So let me see if I can figure out how to show the Google Earth map. So I will try to bring up. Can you guys see Google Earth?
No, we're still looking at the Impress window.
Okay, so then I need to stop share and then go back to share and try to bring this up.
I think so, yes.
Okay, I think I'll try that. Okay, so then in here, I'll go to share screen and try to locate Google Earth Pro. There, can you see it now?
Yes.
Oh, yay. Okay, so this is what it looks like in the vicinity of the Curiosity's working area. And so you can see my APXS zaps and classifications, and they are not following the Google trajectory. And in beige in here, you will see the KMZ produced by Fernando Nogal, and you see that my mapping actually hits his perfectly. When I first saw that, when I put my map together with Google Earth, I had assumed that I had screwed up somehow when I saw this disparity, and darn near killed myself trying to straighten it out. And it turned out that the mighty Google screwed up. And they've known about this probably for 5 years and have not bothered to fix it. So, so to get to different sites, you would you would use, obviously you want to be on the Mars planet, and then under File, you would open the KMZ as opposed to import a CSV. And then you can move around. Let's go take a look at Spirit. A little bit of vertigo. And there they are. And you can see cluster 10, that's the hot pink stuff. That is the area just around Husband Hill. Okay, so so that's the basic K-means clustering exercise. I've done other things with it, but I didn't have the time to go on about it. I used some biodiversity metrics from the biogeography class to characterize the different sites in terms of formal diversity metrics. And so maybe I could come back at some point and talk about that, but I don't have time for that right now. So that's it.
That's fun. I love to see modern statistical methods being used. So, thank you.
What was that?
Are there any questions? I love to see modern statistical methods being used.
Yes.
Instead of just fitting lines, which is a lot of what people default to. Are there any questions?
Yeah, it's kind of funny where the statistical methods came from. I teach this multivariate stats class, and because it's essential to our GIS certificate, the class can always make. And so a lot of other majors want their students to have advanced statistics, but their class won't make. So what they do is they send them over to my class. So I always have this interesting mix of students. I have students from criminal justice. I've got students from psychology. I've got students from archaeology, geology. And so what I try to do is create data sets that appeal to all of them. And so one semester I had a whole bunch of geochem students in the class, and I thought, well, if I'm going to learn a little bit about chemistry, I might as well do it someplace I'm interested in, and that's where I started using APXS on Mars. And that was also really quite a nifty exercise, geomorphic zonation in Gusev crater using principal components analysis. So that's where it all started.